All right, so welcome back, folks. I hope everyone had a good weekend. I appreciate the input from you folks last week about the videos, and so I'll cut down on the amount of review. I realize that we are strapped for time. Just a quick note on the AP exam. I just got message. No, I got information about the exam. They will be cutting down about some of the material, and so we'll be able to cover all the material in time. They're going to cut out the parts of the thermodynamics chapter material, and then they're also going to cut out acid-base chemistry. So we won't have to worry about that. Hopefully, we will get a chance to cover that during class time, though. And so what I'll do is hopefully when we get back, we'll get an opportunity to go over that material, and you'll have that material for you when you get back, when you move forward with your classes in college. Okay? All right, so that's the news. Hopefully, we'll be able to get more of the material done. I'm sorry, I'm going to try to time myself here before I lose track of it. Okay? So that's what's new on the AP front. Outside of that, I think we should be in pretty good shape to finish up chapter 8, and we won't finish chapter 8 until probably Wednesday, Thursday of this week, and so I'll go over. I told you that we'd go over the exam procedures for this chapter, what I would do, but I'm gonna hold off on that, and I'll present the video to you on Thursday. I'll ask you to watch that video. There will be a PhET lab that I'll ask you to do Thursday. That'll involve VSEPR theory, molecular shape, molecular electron geometry, molecular geometry. Give you a bit of a break from my lecturing. And so then what we'll do on Friday is I'll go over that PhET lab with you. I'll do a video, share the material with you. We'll go over VSEPR and review VSEPR at that point. And then we'll review Monday of next week for the exam. And like I said, you'll have the exam procedures presented to you this Thursday, and then we'll take the exam on Tuesday. Okay. So that's what we have moving forward. We'll hopefully get started with chapter 9 roughly Friday. Hopefully VSEPR won't take too long, but I would like to start chapter 9 on Friday as well, and then hopefully get into the last section of this class before your AP exam. Okay, and so the way the AP exam right now is structured is that the AP exam is going to be taken from home. It's going to be proctored. I'm not quite sure how they're going to proctor it, but from what I understand, it's going to be roughly about a 45-minute pre-response exam. So, like I said, as I get more information, I'll pass it on to you. Okay. All right. So with that said, then let's go ahead and pick up where we left off with on Friday. On Thursday, when we were talking about Lewis dot structures. And the importance of Lewis dot structures, folks, is that you need, and you saw the importance of that when we did bond energies. You need the nature of the bonds in order to figure out then determine how the bonds form, what types of bonds form, what types of bonds break. The Lewis dot structure is based upon this localized electron theory, meaning then that the bonds that form, the electrons that form between the two atoms are shared between two atoms, and they stay there. Okay, so the Lewis dot structure, what we're going to draw here, and what we will be drawing, the electrons basically, you'll notice, stay between the atoms that form that particular bond. Okay, all right. So what do you have to do to draw the Lewis dot structure? Well, you got to make sure you are able to count all the valence electrons for each of the molecules first, okay? And then you have to account for all those in the end, making sure then that each atom in the molecule has their 8 electrons. The stability of the molecule is based upon each atom obtaining the electron configuration from the noble gases. And as a result, then all the atoms become stable. And the stability then is what lowers energy for each one of those molecules, thus contributing to more stable state, and thus the atoms want to get together. Okay. All right, so I drew water for you on Thursday. Okay, and so let's go on and let's continue with phosphorus tribromide here. So with phosphorus tribromide, you want to make sure you keep in mind then it's with phosphorus tribromide, you have phosphorus. And so first thing you want to do is you want to count, then make sure then you count for all of the valence electrons. You don't want to count for the total valence electrons. You want to count for the valence electrons. So you have phosphorus with 5 valence electrons. Okay? And then you have 3 bromines. Okay? Each bromine then with 7 valence electrons, but remember you have 3 of them, and so we need to triple that. Okay, so the total number of valence electrons that we have to account for in bromine is going to be then 26. Okay, so when we draw the structures, we have to count all of the electrons and make sure then that we account for all 26. Okay? Now, I think most people will remember then that the phosphorus, if you do this enough, you start recognizing then which atoms are going to be the center atom. Okay, so let's go ahead then. I think from here, then we do all recognize that phosphorus has to be the center atom, because phosphorus then can form the bonds. Okay? And again, if you're not quite sure how we get this, make sure you come by and you see me after school today. Valence has 5, phosphorus has 5 valence electrons, 2 pairs, 2 that are paired, 3 that are unpaired, very much like nitrogen. So bromine, where the valence with the center atom, bromine can only form one single bond, because it has 3 pairs, okay, and 1 single electron, which then forms that bond right there. Okay, and so therefore phosphorus then will form 3. I think most of us would recognize then at this point 3 single bonds with phosphorus with bromine. Okay, with each of the bromines. Okay, and so in the end, and if we draw the dash structure here, in the end, phosphorus will form 3 single bonds with bromine. And if you choose to draw it this way, and from here on out, I'll indicate the number of electrons, but let's go ahead and just to save time, then I'm going to draw the dashed lines to represent the bonds. Okay? With a single bond being 1 dashed line, a double bond being 2 dashed lines, and a triple bond being 3 dashed lines. Okay, what you want to make sure you do then is with the lone pairs, make sure you always include the lone pairs, because these lone pairs will be absolutely important when it comes to electron geometry and molecular geometry. Do not forget to draw in these lone pairs. Okay. All right. So with that said, then that's what we have. And so the localized electron model, what it says then is that these 2 electrons here, they will stay between the phosphorus and this bromine right here. These 2 electrons here will stay with the between the phosphorus and the bromine, and this pair here will stay between the bromine and the phosphorus, and the lone pairs here all stay localized with each one of those atoms. Okay, so that is the 2-dimensional structure for bromine. Bromine has 3 single bonds. Okay? All right, let's go ahead and let's take a look at hydrogen cyanide. Then I asked you to do this. Okay, so hydrogen cyanide, we have hydrogen with 1 valence electron. Okay. We have carbon with 4 valence electrons. And again, after this, I won't do this anymore. I'll just write it out for you, but make sure you're able to calculate for these here, folks, because you want to keep track of this. And nitrogen with its 5 valence electrons. And again, these are all valence electrons, not total number of electrons. This valence it's the valence electrons that participate in the bonding and in the interactions between atoms. Okay? All right, so therefore, then we have to account for 10 electrons. And I'm sorry, let's go back up here and count to make sure we have 26. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 13 pairs to 26. Okay. All right, let's go ahead then. Let's do the same thing for hydrogen cyanide. Okay, so carbon then. And what you're going to notice here, and keep this in mind, whenever you see carbon as part of a molecule, carbon will always be the center atom. Okay? With very, very few exceptions. Carbon will be the center atom. Okay? All right, so carbon then, we remember from first year chemistry, even though when we draw out the atomic structure for carbon, we have 1 pair and 2 unpairs. We talked about how each one of these electrons here are fit into a hybridized orbital. We'll talk about hybridization much more in chapter 9. But because of hybridization, then these 4 electrons will spread out. Okay? All right, so with that said, then nitrogen and hydrogen will surround it. So I think we can see this here with 1 bond here. Okay, and then nitrogen then, and I'm going to draw it this way, is it has its 5 valence electrons. Okay? And then I think if you see this here, if you have a triple bond that exists between the carbon and the nitrogen, then all atoms will achieve either their duet in the case of hydrogen, or the octet in the case of nitrogen and carbon. Okay, and so there's what we have. And finally, if we count all the electrons, we will have 10. So we have 1, 2, 3, 4, 5. 5 pairs, there's going to be 10 electrons. Here then, a triple bond forms between carbon and nitrogen, and a single bond forms between hydrogen and carbon. Okay, and so with the Lewis dot structure, folks, what you want to do then, just as a recap, make sure then you count the total number of valence electrons, and then start connecting dots. Basically, you want to connect the dots to count then to make sure then in the end all atoms have their 8, or in the case of hydrogen their 2. That's the octet and the duet rule that we talked about. Okay, and if that's the case, then if the structure you end up with needs to put all those. Don't forget to include also the lone pairs. Then you have the correct structure. Okay, all right. Very good. So what I'd like you to do then is let's go ahead and let's take a look at what I'd like you to do moving forward. Oh, okay, I'm sorry, there it is. Okay, we got there are the structures. Sorry. Let's go ahead then. I would like you to draw the structures for these 3 molecules here in number 8. Okay, so go ahead and draw these here. Take about a couple minutes. I don't think they should take you too long. Take a couple minutes to draw it. Do not forget to include the lone pairs. And then at the end of 2 minutes, come on back, hit the start button, start the video again, and then we'll go over. Okay, so draw these 3 structures on your paper. Okay, let's go ahead and let's take a look at these 3 structures and let's work them out fairly quickly. I think here you recognize that you have 2 electrons that you have to count for each hydrogen. Then it's going to be connected by a single bond, a single covalent bond, 2 electrons between them. Both then achieve their duet. Okay. Fluorine, on the other hand, fluorine, you have to count for 14 electrons here. So for fluorine, make sure you keep this in mind. Fluorine then, for hydrogen, we had to count for 2 electrons. For fluorine, we're going to have to account for 14 valence electrons. Okay, so let's go ahead and write that out. Between each fluorine, then, if we have a single bond, that makes only 2. There's a total of 14 that we have to account for, which means that we have to include in the lone pair electrons. Okay, so let's go write those in. Okay, and we have our 14. 1, 2, 3, 4, 5, 6. There's 12, and these 2 here, that makes it 14. Okay. All right, for the hydrogen fluoride molecule, then, we have to account for a total of 8 valence electrons. And so I think we can recognize then that the single bond then between hydrogen and fluorine can only account for 2 of those 8. Okay, therefore, then we have to include in the lone pairs there. And there is 1, 2, 3, 4, our 8 valence electrons. Okay, so please make sure you write in these structures here. Okay, and then be ready to submit that towards the end of the period. Towards the end of at the end of this video. Okay. All right. So let's go ahead then. Let's do another one. Let's try another one here, and I'd like you to do number 9. Try number 9 in your problem set. A couple minutes. Okay. And then I'll see you back here when you come back. Okay. All right. Let's go ahead and let's take a look at. Let's do ammonia first. Okay. So NH3. We have to account for within H3. We have 8 total electrons we have to account for. Okay, so nitrogen is going to be the center atom. Okay, I think that if you recognize that if you form a single bond between the nitrogen and each of the hydrogens, you will account for the 8. Each the hydrogens have their duet, and the nitrogen has its octet. So yeah, 1, 2, 3, 4. There is your 8. Okay, all right. Let's take a look at carbon dioxide. Okay, so we have then 12, and 5 is 17. 17 electrons. I would say 12 and 4 would be 16 electrons. Sorry, okay, we have to account for. Carbon, like I told you, will always be the center atom. Okay, make sure then that you can see why we have a double bond that's going to exist between each oxygen and the carbon. Again, make sure you draw, if you need to draw out the actual dots themselves and the connected dots, go ahead and do so. But then if you do so, you can see that it's going to be a double bond that connects each oxygen to the carbon. And if that is the case, then we have counted for the 16. So let's go ahead and count to make sure. We have 1, 2, 3, 4, 5, 6, 7, 8. There's your 8 pairs for 16 electrons. Okay, okay, carbon tetrachloride, CCl4, CCl4 in the end. Okay, so we have 28, 29, 30, 32 electrons we have to account for here. So 7 electrons for each chlorine. We have 4 of them, so that's 28 plus 4 is 32. Okay, so carbon tetrachloride, you're going to see then that carbon's going to be the center atom again. Single bond between the carbon and each chlorine, because chlorine can, all the halogens can only form a single bond. Okay, they only have 1 pair to share. Okay, and so with that said, then we only have 1, 2, 3, 4, 8 electrons. Therefore, there are valence electrons that are non-bonding electron pairs that are not accounted for. Let's fill those in. Okay, and then we should have our 32. So 1, 2, 3. 3 and 4 is 12, 24, 25, 26, 27, 28. I'm sorry. So 3, 1, 2, 3, 3 for each chlorine, 12 total pairs. That's 24 plus 2, 4, 6, 8, 8 more. There's our 24, 32. Okay. All right. So with that said, then let's make sure that you're able to draw those structures. Okay? Those are the simple structures that you have to be able to draw. Please practice them. Tonight's homework, I'm going to ask you, I'm going to assign the homework. We'll have formal charges in it. Please don't, the formal charges we'll talk about tomorrow, but do try drawing the Lewis dot structure. Okay? All right. So with that said, then let me ask you to consider a compound, okay, such as, sorry, let me go ahead and do this here. Okay, such as boron trihydride. Okay, so we'll consider that in just a moment. The problem with the localized electron model, and I already pointed this out to you, and the problem with this localized electron model is that because it's overly simplistic, it doesn't help to explain everything that we come across. Okay, and so it's easy to understand, but it also, because it's simplistic, there are going to be plenty of exceptions that we have to deal with when it comes to using localized electron model, explain structures and properties of these molecules. Okay, all right. So with that said, then, if you keep in mind what we have there will be instances where we have to take into account atoms that will not achieve their octet. And so, like I said, let's take a look at boron trihydride as an example here. Okay, boron trihydride has a total of 6 electrons. Okay, boron and 3 hydrogens. With 3 hydrogens, then I think we should pretty much recognize that the boron will be the center atom. Boron has 3 valence electrons. Okay, so let's go ahead and draw those in. It has 3 valence electrons here, and because of hybridization, they're going to spread out. The hydrogens then will each go in, form a bond with each one of those unpaired electrons, and then that's it. There are no more valence electrons, and there's your total 6 valence electrons. There are no more valence electrons available for boron. And so here, each hydrogen achieves its duet. So each hydrogen on the is stable here based upon its electron configuration and its similarity to helium. But boron here is deficient. Okay, boron here is deficient. So there will be compounds where some atoms will have deficiency in electrons. Typically, we'll see that with boron. The examples that you'll come across in freshman first-year chemistry will be boron. Beryllium, sometimes when it does form covalent bonds, will also not achieve its octet. But for the most part, then, this exception here is going to be pretty much limited to just boron and one other element. And occasionally, you're going to see then that yeah, I'm sorry. Let's just keep it at that. Okay, so you're going to see that happen as well, and that has to happen because boron will form covalent bonds, but it will never achieve its octet. Okay. All right. So with that said, then you will, if that's the case with atoms that achieve less than their octet, let's take a look at. So there's the compound there. What about these compounds here? Okay. Sometimes you're going to see then in certain compounds atoms that will exceed the octet. So these are exceptions. We're going over the exceptions to the octet rule because, again, the localized electron model is overly simplistic. We're going to have these exceptions. So if you notice in both of these elements here, we have, in both of these compounds here, we have elements that are in the 3rd row or higher. And typically what you're going to see then when you have compounds in which you have elements that are in the 3rd row or higher that takes place that participate in the bonding. Sometimes you will see an exception to the rule in that you'll have some of those elements exceed the octet. Now, what we typically do in that case then is if that does happen, we always assign the extra electron to the center atom. So the central atom, we're going to go ahead and place the extra electron. Okay, all right. So here I think you can recognize in that sulfur will be the center atom. Okay? And fluorine will form a single bond with sulfur. Each fluorine forms a single bond with each sulfur. Each fluorine, remember, will have a total of 3 pairs. We draw that in as well. So there are 3 pairs for each fluorine. Okay, so there's where we have it. Okay, so with that said, then we have 1, 2, 3, we got 12 pairs is 24, 25, 26, 27, 28, 29, 30, 31, 32. we have to account for a total of 34. So 32, 2 extra electrons have to be accounted for, so we can place those 2 electrons simply on the sulfur there. And when we get to VSEPR and we draw these configurations for these molecules here, you're going to see then that these electron pairs here will fit into their own space. Okay. All right. Same thing holds true for arsenic here. So let's go ahead and draw arsenic here. Arsenic's going to form a 5 single bonds with bromine. Okay. Again, with the halogens, you can only form single bonds, so make sure you keep that in mind. That's why we're going to go ahead and draw it this way. Okay, so there are 5 single bonds. Okay. Each bromine will have 3 pairs. Okay, so we'll draw that in. Our 3 pairs there, 3 pairs here, and 3 pairs here. Okay, and so if you total up, so we have the 3 pairs for each bromine. We have 5. That's 30. 2, 4, 6, 8. That's 38 total. We're still deficient in 2, so we just take the 2 pairs of electrons that are left over and place on arsenic, and that will give us then our 40. Okay, so I'm sorry. Let me back her into it. 1, 2, 3, 4, 15. 2 is 30. Sorry. Okay, 30. 2, 4, 6, 8, 2, 4, 6. There's our 40. I'm sorry. So I overcounted. But if you notice here, then we have an excess of electrons on the arsenic. Okay, so we don't have to place those 2 in there. And so the arsenic then will have 10 rather than the 8. Okay, so in both cases, you have an excess of electrons. Okay. So just to sum up here, then, just to finish up here. Okay. If you have, I'm sorry, there's that, and there we have that. Okay. All right, so you maybe wondering then, will there be cases where, can we figure out what the exceptions are? And I think I shared this with those folks who had chemistry with me before. There are certain atoms that will always obey the octet rule for various reasons, for various reasons of stability. There are. So what you need to keep in mind then is carbon, nitrogen, oxygen, fluorine, and I would extend that to include almost all the halogens, but carbon, nitrogen, fluorine for the most case will always obey the octet rule. Other atoms may either have a deficit or deficiency of octet, or may have less than 8, or it can expand its octet, which means it will have more than 8. Beryllium and boron can have less than 8. So these are generalizations that you can use to help you. Okay. Second row elements, so like I said, never exceed the octet rule. In the third row and higher could exceed the octet, thus expanding the octet. So these general rules work for the most part, and I think you can go ahead and use this. However, with that said, then if an atom can achieve its octet, whether it's in the third or fourth row, doesn't matter. If it can't achieve its octet, if the atom can achieve its octet, it will. Okay, so make sure you keep that in mind. So when you write your Lewis dot structure, try to make sure that all the atoms achieve their octet first. If you have electrons that are left over, or if you have to expand the octet, you go ahead and do so, but only for the center atom. Okay. So basically, what you're doing is you'll be placing those electrons into the d orbitals of these period 3 elements higher. Okay. All right, so what I'm going to do is I'm going to stop there. I'm going to assign the homework for tonight. Okay, no extra, and I'll assign the extra problem for you in just a moment. Please go ahead and try that. Submit the paper, and then try the homework for tonight. Don't do the formal charge yet. We'll do formal charge tomorrow, and then come on by and see me if you need help and extra review how to draw these Lewis dot structures more. Okay. All right, folks, so good luck with the work, and like I said, come on by and see me if you have any questions after school today, okay? If not, I will see you folks tomorrow, okay?